Hello, today it's my pleasure to talk about raising stress, dealing with stress raisers in some pretty simple situations. And the moral of the story is don't be off by a factor of 2 or KT. Remember your baseline theory for dealing with static loading. If it's a ductile material, you use yield strength. If it's a brittle material, you use ultimate strength. And then there's this notion of what do you do with the stress raisers? There's the KT or the KTS. You do use them when it's a brittle material, and then there's the issue of what do you do with them when they're ductile, and we'll talk about that. Let's take a very simple stress concentration scenario where we've got a hole in a plate and we're stretching the plate with a tensile force longitudinally. So it's a uniform normal stress scenario. And depending on what the diameter of the hole is with respect to the width of the plate, you get various stress concentration factors KT that amplify the nominal stress. I think in the example I had, I used 0.3 for D over W. So it should be about 2.35 for the KT. So the stress does get raised near the hole, no matter if it's ductile or brittle, the stress is always raised. It's just that for ductile material, the raised area stress is actually cold work and strengthen that area around the hole. So what I did is I generated a representative part in SOLIDWORKS, and then I stretched it and did an FEA on it. And you can see here what the stress plot looks like. It's a color one. I like this. And you can see nominally green. What the green looks like is the nominal stress value. And then near the hole, there's one part of the hole that gets stretched. So the circle of the hole goes more like an ellipse. So the top part gets stretched and it's red, tensile, and the sides get kind of pinched, compressed, so it's blue. So blue is a very low stress, red's a very high stress, and based on my numbers, it was about right. Whatever the nominal value was, the red was about 2.3 times higher. So it worked out about right. The normal force F creates a uniform nominal stress sigma naught that acts over the minimal throat area, which is the width minus the diameter times the thickness of the plate. So that's the nominal stress, and then as we discussed, that's amplified near the hole by the stress raiser KT. So that is a principal stress because there are no shear stresses acting on that face. So by definition, it is a principal stress. And the other thing is in the vertical direction or in the direction perpendicular to the plane, there's no stress. There's no load. There's no nominal stress. So sigma 1 is a tensile stress. So it is KT times sigma naught. Sigma 2, since there's no load vertically or perpendicular to the plane, sigma 2 is 0 and sigma 3 is 0. So it's a very simple Mohr circle to draw. We've just got the sigma 1 with no associated shear there. We've got sigma 2, sigma 3 at the origin. And it's very simple to draw the Mohr circle here. If we kind of proceed and think about, well, what is the max shear in this situation? Well, the max shear is going to be the top of the circle. It's pretty simple. In this particular relationship, sigma 1 minus sigma 3 over 2, if you do the convention of sigma 3 being min, sigma 2 in the middle, sigma 1 is the max, if you maintain that convention, then the maximum shear is always sigma 1 minus sigma 3 over 2. It's going to be the radius of the biggest circle. And in this case, tau max is going to be sigma 1 divided by 2 because sigma 3 is 0. One of the things I like about Mohr circles, it gives you a chance to look at a particular loading from a different direction. And I've identified a red direction here that's 90 degrees offset from the sigma 1. And then there's the other one here is offset 90 degrees from sigma 2, sigma 3. And what that looks like, since Mohr's circle is a double angle, that's actually related to 45 degrees in the real stress element. So the 45 degrees here for this face and this face corresponds to that point. So we've got sigma 1 over 2 being the normal stress on the positive face and then the negative face. And then we have for our taw, it's going counterclockwise on those two faces. And then the other point also sees a sigma 1 over 2 normal tensile stress, and it's going it's a tensile stress going on these two faces, and then the direction of the taw is actually clockwise for those two faces. So I really like that, and this gives you an idea of why it's called max shear stress theory for ductile materials. Failure is actually predicated on planes that slip at 45 degrees to the direction of pull, and it gives you an idea of why it fails by shear. For ductile, so we take max shear stress theory, and you have SY divided by 2 taw max, and then I substitute in what my taw max is, and then I can simplify a little bit because the 2's cancel. This is another representation of max shear stress theory, yield strength divided by sigma 1 minus sigma 3. And then in this case, since sigma 3 is 0, I get SY over sigma 1, and then I plug in the KT times the sigma naught. And the thing in the book, it says, hey, if it's a ductile material, we treat that KT as 1 for the purposes of determining our factor of safety. So that's a very nuanced discussion. Remember, the stresses are there. That sigma 1 is there. It's red like I showed you. But since it's strain hardening, the book says to go ahead and treat for the purposes of calculating your factor of safety. Go ahead and treat that KT as though it's 1. They call it unity, same thing. So that means that in this case, our max shear stress theory is going to, factor of safety is going to be SY divided by sigma naught. And this is uniform normal stress for ductile. It sets what our factor of safety is going to be in this scenario. On the other hand, when it's a brittle material, we'll rely on the book's definition for brittle Coulomb-Mohr. It's given in a reciprocal form. 1 over n BCM is going to be sigma 1 over SUT minus sigma 3 over SUC. And these are tensile and compressive ultimates. When they're the same, it can simplify to just n BCM is SU over sigma 1 minus sigma 3. In this case, well, let's say that they are the same. In this case, we're going to have SU divided by sigma 1 is our NBCM, and we're going to substitute in the KT sigma naught for my sigma 1, and we are going to use the KT value when it is a brittle material. So that sets our NBCM is SU divided by KT times sigma naught for our uniform normal stress in the brittle scenario. So simplistic static failure theory, and this is when you have the uniaxial or normal loading, uniform normal stress. You only have one principal stress. And if it's a ductile material, the material looks like it shears at 45 degrees when you pull on it, and the factor of safety is SY divided by sigma naught. If it's a brittle material, you want to use SU, and it breaks like a wafer cracker. You take SU divided by KT times sigma naught, so you do use the KT to get brittle Coulomb-Mohr factor of safety. We can think about a pure shear stress scenario by looking at a solid round rod that has a hole in it that we're applying a torque to, and that's going to create a shear stress that's going to be maximal on the outer surface of this solid round rod with a hole. So there's a nominal shear stress, tau naught, and it's calculated as follows, where the big D is the major diameter of the rod, and the small d is the diameter of the hole. The ratio of D to D sets what the KTS, the shear stress concentration value, might be. And I think for my example, I used 0.2 that I generated in SolidWorks. And the book gives us two different graphs, one for a point that is a point B that is on the outside diameter, and then one for a point A that's a little bit inside the hole. So that's why there's a difference. And again, it doesn't matter whether it's ductile or brittle, the stress is raised near that hole no matter what kind of material. For ductile material, the raised stress does cold work it and strengthens that area. So we're going to treat this about the same as we did for the normal stress. So here was my mock-up in SolidWorks. SolidWorks, unfortunately, doesn't plot max shear stress, but they plot something very close. It's called stress intensity, and it's actually the difference of sigma 1 minus sigma 3. I'm calling it sigma sub I. So I see that difference, and I know that that's twice the max shear stress. And in my numerical example, I estimated that my tau 0 would be 6 kpsi. So that means that the nominal stress intensity would be double that, or 12. And you can see a lot of green here. So we're right there in the nominal range. So I felt like, pretty much had it modeled right. And what I did is I did a section cut there at the hole so we can kind of dive in. Now on the graph in the book with the D over D being 0.2, let me go back and look real quick. 0.2 should have been about 2.7-ish, maybe 6, 7. Yeah, 2.7 for the B point. And didn't quite get that high. So what I did is I did the graph from 0 to 24. So had I seen any red, that would have been a KTS of 2. But it really only shows up to about 20. It is elevated, I can see that. So what the SolidWorks is showing is probably more like about 1.7, but it is elevated. To be conservative, I'm just going to use the book's values as we move forward here. So if we go and do the same thing we did before with trying to do a simplistic example and more circle, we can say that on the surface, I've only got shear. That's all I've got. I've got no normal stress. There's nothing doing that. So that shear that I have, which is KTS times sigma, times tau naught, that tau max that I have, that's it. So it has to be a principal shear stress. There's no principal stress. There's no normal stress. So what that means is that the purple shear element here must have these points. There's no sigma. There's no normal. So that's going to set my circle straight away. And I can easily draw in the other more circles, and I've shown them in red. So this easily sets what sigma 1 is and sigma 3. And then sigma 2 is going to be, it's going to be a plane stress scenario, as I'll show you in a moment. So it's going to be 0. So if I maintain that same convention, you see that sigma 1 is plus whatever my tau max is, and then sigma 3 is going to be minus that tau max, and sigma 2 is 0. And again, I've got this 90-degree thing. So I said, well, what's this thing going to look like, if I were to cant it at 45, look at, this stress element from a different direction. 45. Remember, there's a double angle between the Mohr circle and the actual element. So when I get to the 45, there's no shears. There's no shears for the red. And I've got a normal stress, sigma 1, normal principal stress, sigma 1. And then I have this sigma 3, which is actually compressive. So this is what it's going to look like. Okay, max shear stress theory for ductile material in this scenario. We start with our definition. We substitute in KTS times tau naught. And then we remember that the stresses are elevated. The tau max is there, but it's just strain hardening in that area. For the purposes of calculating an MSS, we set the KTS to 1, as the book says. And that sets our pure shear stress scenario for ductile materials. That sets our factor of safety, according to max shear stress theory, is SY divided by 2 times tau naught. Okay, now for a brittle material, remember we have our NBCM is SU divided by sigma 1 minus sigma 3. And in this case, when we substitute for sigma 1 and sigma 3, we substitute tau max for sigma 1 and minus tau max for sigma 3. We actually end up with SU divided by 2 times tau max. And when we substitute for tau max, our KTS times tau naught, we end up with our answer. And for the pure shear stress scenario for brittle material, the theory says, according to brittle Coulomb-Mohr, that the factor of safety is SU divided by 2 times KTS tau naught. So let's put it all together. So we've got two different kinds of very simple loading. Either we have a uniform normal stress, uniaxial loading scenario. We've got a pure shear stress scenario for loading. So you have two different kinds of loadings. And then we have two different kinds of material we're talking about today. We're talking about a ductile material that's going to use max shear stress theory. And then we have a brittle material, which is going to use brittle Coulomb-Mohr. So as I was saying initially, the opening here, it's easy to be off by a factor of 2. And it's also easy to be off by a factor of KT. So let's kind of review these things quickly. The first thing is ductile material. You're going to use SY, yield strength. Brittle material, you're going to use SU. If it is a ductile material, no KT. If it's a brittle material, you're going to use KT. If it's a normal loading scenario, uniform normal stress, there's no 2, and there's a sigma. If it's a pure shear stress scenario, there is a 2, and there's a tau, shear stress that goes with it. I'd like for you to enjoy my little cartoons. If it's a brittle material that is being pulled in uniaxial loading, it breaks like a wafer cracker if it's brittle. And if it's loaded in pure shear, breaks like a wafer cracker. On the other hand, if it's a ductile material, uniaxial loading, uniform normal stress, you pull on it, you see the slip planes at 45 degrees, just like I showed you in the Mohr circle experiment. And if it's in pure shear, what you see is the same sort of slipping occurring, but if you look at what's happening between the rectangles in this direction, they're getting compressed, so that looks like a compressive normal stress, versus the rectangles in this direction are kind of being stretched a little bit, so that's the tensile principal stress. So it all kind of comes together here in this one slide, the things we've talked about today. And if you can navigate those things, then you've won the battle. I hope you've enjoyed it.